we can start with the basics. Can you kind of give an overview for us of what quantum computing is and kind of the state of play of things right now?
Yeah, absolutely. So quantum computing is a new kind of way to build computing technology. So everything we have today in computers, which is incredible, what you can do with computing today, is fundamentally based on a transistor, a special kind of switch that can be 0 or 1. Quantum computing kind of asks, what if your switch was a quantum mechanical object, something that obeys quantum laws of physics, can do very strange things, and what if you rebuild how you compute based on that? And so if you do that, it turns out, if you can build such a device and you can integrate it into a supercomputer, you can start to solve problems with computing that we just wouldn't have even thought of as being addressable. They were just too hard or outside of the scope of computing. So it's really a new kind of technology that augments our existing kind of GPU supercomputers with whole new capabilities.
And is it that, and you're going to have to correct me here as we go, sure, but to kind of break it way down, is it that quantum allows for faster computation or more computations at once? Something different? How does it work in that regard?
Yeah, so in some application areas, it might be that it can perform some things faster than a conventional computer can, but that really undersells the difference. In many cases, it's so much faster that the problems just were not tractable at all. It wasn't that, today's technology was a bit slow, maybe some future generation would be. In some cases, quantum computing can give us a kind of exponential or even like a very strong polynomial advantage over a normal computer, meaning that as you make the problem you're trying to solve just a bit bigger, very quickly it becomes just impossible on any other kind of computing device. But an important caveat is that quantum computers or quantum hardware isn't necessarily better for all kinds of applications. Okay. There are some very specific areas we know where it can be really transformative, but crucially those are areas that we really care about.
And so what's kind of the current state of the art with quantum? Are people using quantum computers to start to solve some of these problems? Is it more in the R&D stage? Where are we at with things?
Yeah, so we're at a really exciting point because today people are building quantum hardware. They've been doing that for a while, but we're really seeing an inflection point where we're transitioning from kind of experiments or sort of demonstrative systems to the larger scale kind of systems that you need and that you can kind of integrate with supercomputing to start to solve some of these really promising and important problems. Things like developing new drugs, simulating and developing new kinds of materials. Those are all things that we can't quite do today with quantum computing, but the kind of progress we're seeing, like literally this year, what people are starting to work on, really kind of brings those into focus. And we think it, might not be too long before we can build systems capable of realizing that promise.
Before we get deeper into some of the applications, kind of looking forward, what are the current challenges to building quantum systems?
Yeah, so when you try and build a quantum processor, as we call it, a QPU, quantum processing unit, that unit uses, instead of bits like you'd use in a normal computer, it uses what we call quantum bits or qubits. Yeah. They're very difficult to control and to keep going, basically. They experience a fundamental kind of noise, and you have to continually kind of try and correct them. And that process is called quantum error correction. And it's really important because all of the big applications people talk about for quantum computing kind of assume that your qubits are not noisy.
Right.
And so one of the big challenges in building useful quantum hardware that can, do useful quantum accelerated supercomputing tasks, one of the important things is to be able to master quantum error correction. And so that's a big challenge. And that's actually something at NVIDIA that we're working towards, because a huge part of performing quantum error correction is a conventional kind of algorithm or computation you need to run called a decoder that kind of enables the quantum error correction. Okay. So there are a lot of challenges we still face to scale up quantum computing. And in fact, some of those challenges are ones that can seem very familiar to the kinds of advances we already know about in supercomputing and classical computing.
Right. So kind of along those lines, how is the advent of AI shaping the development of quantum? And I mean, can you use AI to help with things like error correction?
Yeah, so that's there's actually many areas where it increasingly looks like AI is going to really unlock progress in quantum computing. It's going to allow breakthroughs. Yeah. And a key one of those is quantum error correction.
Okay.
So when you do quantum error correction, if you sort of double click on it a little bit, what happens is your qubits are noisy. You can't just the trick with qubits, which I haven't explained at all, but you can't just look at them, because if you look at qubits, you destroy the kind of quantum information in them. You have to isolate them for them to work correctly.
Okay.
So you have to be very measured and purposeful and kind of restricted in when and how you interact with them.
Okay.
Yeah, go on.
Can I back up a step?
Yeah, you can back up.
Okay. Tell me about this whole, if I look at it.
Yeah. So the way a qubit works, let's talk about a qubit a bit.
Please.
Because it will make quantum error correction clearer. So the way a qubit works is that instead of just having a 0 or 1, like in a transistor, if you think of it like a switch, it's 0 or it's 1, you can kind of have what's called a superposition of the two.
Okay.
Now, people like to say that means it's both a 0 and a 1.
Right.
It would be great if it was that simple, but it's much more weird than that. It's hard to explain, but it's a kind of combination of the two, but it's a very delicate combination. And it's fragile, and if you go in and you touch the qubit or something bumps into it, or it interacts with its environment, you'll destroy that delicate superposition that you will have engineered correctly to do your quantum computation.
Okay.
And so quantum error correction seeks to do what seems impossible, which is to look at those qubits to find out if they're correct, if they've got errors in them. But at the same time, you don't want to touch them or look at them.
Right.
And so the geniusness of quantum error correction, when it was discovered, it was a turning point, because before that, people thought quantum computers would be just too noisy, you couldn't build them. And then some very clever people discovered in the 90s that actually, if you have a lot of qubits, you can link them all together in a special way. You can, what we call, entangle them, and you can look at some of them and you destroy those ones, you sacrifice them. Okay. But in return, you learn just enough about the other ones through the kind of links between them to learn where the errors are, but without having disturbed them enough for it to really matter. And so that's the way quantum error correction works.
Right. Okay.
But to do that process, what you end up having to do is to look at some of your qubits. You get information from them, you get data, and then you have to do a kind of Sherlock Holmes calculation. You have to process that data and infer, retrodict, where the errors must have been for you to see that data, and then go in and do some corrections thousands of times every second. You have to keep doing this or it'll fall over.
Right.
And that inference algorithm, the Sherlock Holmes algorithm, is the decoder.
Okay.
And that's very hard. It needs to process terabytes of data. Like I say, you have to do it thousands of times a second. You have to get the data out and back in very quickly, or you end up with a backlog and you build up and it all falls over. Yeah. And so decoders are one example of a task in quantum computing that we think AI, or we are seeing that AI can have a really big impact on.
It sounds like it, yeah. Are there things that are stopping, or maybe a better way to phrase it, researchers who've been working on quantum? Are there hesitations about using AI in the process? Are there specific roadblocks or hurdles that have to be overcome? How does the whole, because the way you describe it, in describing you have to do this same process over and over again very fast, it's like, oh, AI is great for that. Yeah. But what are some of the challenges, specific to bringing AI into quantum?
So there are challenges, and it's really important that we figure out those challenges, because the example I just gave you was just one. Yeah. There's other areas where we think AI is going to be really important. So calibration. So if you have to keep tuning your quantum hardware, which sounds similar to quantum error correction, you keep trying to fix it, but it's a little different, and it's also hard to do.
This is a naive question, sorry, Nick, but the hardware itself, is it materially quite different than transistor-based computer hardware?
Yes, so it is. So like a quantum processor is a kind of entirely new kind of hardware. So the people who build these, and NVIDIA does not build quantum processors, but we work with a huge number of partners that do. In fact, almost everyone trying to build it in one way or another, we work with them. Right. They're trying to build something entirely new. They try and utilize existing techniques as much as they can, but it's a new kind of technology. And an important sort of caveat of that is whereas with the transistor, we really settled on the transistor as the way to build a computer, or the way to build a bit. There's lots of different ways people are trying to build qubits. Okay. And so what's really important, if you think of, for example, building AI tools to help with quantum computing, is that you can kind of accommodate all those different approaches. And so that kind of leads into one of the biggest challenges that researchers face with AI tools, is just getting access to them. Yeah. So they need very open tools, because they might need to retrain or fine tune those models for their specific kind of hardware, because there's different approaches. Right. And just generally speaking, having open models really opens access to this whole broad quantum ecosystem.